Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 9 academic students who are studying the measurement and geometry unit. In particular, this is part 2 of the unit where we look at three-dimensional measurement, and this is video number 1 of that part of the unit. So what do we look for when we study three-dimensional measurement? Well, this year we're going to study volume. So we're going to look at the formula for volume and various volume questions, and we're also going to study surface area. Again, we're going to look at their formula, and we're also going to study some questions. And let's start with just volume first of all. Again, you do have a formula sheet for this entire unit that you're welcome to use for every quiz or test or the EQAO itself. And here's what the formula sheet looks like. It's fairly busy. You'll notice it has 6 shapes on it for us to talk about. And I want to start by focusing on volume only. So here are 3 shapes from that formula sheet: cylinder, rectangular prism, and triangular prism. And we're going to start our discussion by looking at those 3 shapes only. And what you'll notice about those 3 shapes is, first of all, I've given you some real-world examples. So a cylinder, we all are probably familiar with things like Coke cans. This particular type of water, which actually to me looks like it's more like a shampoo bottle, is a really nice looking cylinder. A rectangular prism, of course, we often think about a box. And a triangular prism, well, we like to think about perhaps the Toblerone chocolate bar container as an example of one of those. And what I want you to notice, the reason why I've pulled these 3 shapes together in particular, is that all of them have this comment or this statement about the volume, that they're all measured as the area of the base times the height. So really what they're saying is that if you look carefully at this formula, what you should see is the base is a particular shape, and that gets multiplied by height. So we have a circle is the base of a cylinder times the height. So pi r squared is the circle times the height. A rectangular prism is just a rectangle times the height. So you can see length times width for the rectangle, and then times the height. And a triangular prism is a triangle. So base times L divided by 2, and then multiply that by height. Now, you might find it strange that we're using L here when in 2 dimensions we always use the letter H. But obviously we can't talk about 2 different types of heights. So they've gone with a convention of calling this the base still, but now this is L. I'm not sure why it's an L, but it definitely can't be H in the 3D world. So here's a closer look at where some of those formulas came from. Excuse me. This is obviously a rectangle, and right now it's a 2-dimensional rectangle. What I need you to do is I need you to see this in a 3-dimensional setting. So the best way I've discovered to do that is I'm going to take this rectangle and I'm going to put it on my desk. So do you now see this 2-dimensional rectangle exists in a 3-dimensional world? Good. And what I'm going to do is I'm going to start to pile identical rectangles on top of each other. So I started with one, and then there's another one, and there's another one, and there's another rectangle, and let's see. And then here's a pile that I kind of cheated on and made it in advance. Oh, except for I have to order it properly. And what I want you to notice is this is now an object that is clearly a 3-dimensional object. So even looking at it from a 2-dimensional computer screen, you can see that this is an object that has a dimension like this, a length, a width, and there's a height to that object. And what you should have noticed is that if I wanted to calculate the volume, so the amount of space that this entire pile of rectangles takes up, what I could do is I could tell you, or I could calculate the area of the bottom triangle, so that very first triangle, which would be length times width, and then say that I need to multiply that by the total height of how many rectangles I placed there. So again, it's a 3-dimensional object that started 2-dimensionally, length times width, and then when we piled it up, we created the 3rd dimension called height. And that's where this formula, length times width times height, comes from. The same idea for a cylinder. So again, here's a circle. And again, I wanted you to see it in 3 dimensions. So at this time, I took this 2D circle and I put it onto my IKEA coffee table. And hopefully you can see this is now a 2-dimensional circle that exists in a 3-dimensional world. And so again, I'm going to start stacking identical circles on top of each other. So what I'm doing is I'm trying to take this 2-dimensional object and by stacking it, give it a 3rd dimension. And hopefully you should start to see a cylinder take shape. So what you should see is we started with just a 2-dimensional circle on the bottom, but now we have, sorry, I keep pressing some button. Let's hope that doesn't keep happening. So we now have a bottom or a base that is circular shaped, but then we now have a height. So if I wanted to calculate the volume or the amount of space taken up by this object, then I could say that it started off as a circle and then it developed a height. So that's how we get a volume equal to pi r squared h for a cylinder. Now, to talk about a triangular prism, I could do the same thing. I could, pretend that I'm stacking triangles, but this time I'm going to pretend that I'm taking this object and I'm slicing it, so kind of working the other way. And you can see that every time I slice it, I'm creating a 2-dimensional triangle. And effectively, this prism is just a whole bunch of skinny triangles stacked on top of each other. So that'll give us, if we think about this as the height, and then I have base, which is triangular shaped, and we know that the area of a triangle is base times L divided by 2. So that base shape has an area like this, and then if you stack a whole bunch of those triangles, like we've done here, then you can find the volume by multiplying by h as well. So let's look at some of the other shapes that were on the formula sheet. Well, there's a cone. So we all know a cone, an ice cream cone, that sort of thing. And have a look at the formula for volume. It also says area of base times height, but then it says divide by 3. And if you look here, you are given a choice as to whether or not you use this formula or this. I'm going to talk about this one. It's the same formula mathematically, but I like the looks of this one better. Because when I look at it, what I clearly see is I see cylinder on top. That pi r squared h, pi r squared h is what we were seeing when we were studying the cylinder. So this is basically a cylinder divided by 3. And the reason why is something that you may have explored in an earlier grade. So again, here is a cylinder. So the cylinder represents pi r squared times h. And if you were to take this cone, fill it with water, and pour the water into the cylinder, then you would discover that the cone holds exactly 1/3 of what the cylinder can hold. That's why you take a cylinder and you divide by 3 to get a cone. Again, I'm hoping you did that exploration in an earlier grade. So it may have involved water, it may have involved sand, but what you're doing is you're confirming the fact that when these two objects have the same height, so when they have the same height like this, and when they sit on the same circular base, then the cone is exactly 1/3 of the cylinder. And that's why the formula is exactly 1/3 of the formula for cylinder volume. Same thing is basically true with a square-based pyramid, except for now, the top of the fraction is the formula for a rectangular prism with a square base. So if we have a rectangular prism, so here's the visual in a way, a rectangular prism with a square base. So if both of these shapes have the same square base and they share the same height, then again, this pyramid will hold exactly 1/3 of the volume, so sand or water, as the actual prism will. And that's why you see divide by 3, because it will hold 1/3 of the amount of material. There's more information about these things, and I think there's actually also a animation at this website that you might want to check out. And then there's one final shape to talk about, and that's the volume of a sphere. Oops. So the volume of a sphere, again, you have two choices, and I like this choice personally. It's 4 pi r cubed divided by 3, and that cubed is really important. I see a lot of students who don't look very carefully and write that as a squared, and then obviously you get the math wrong. So make sure you notice that it's 4 pi r cubed, meaning r times r times r, and then divide by 3. So why is this the formula? Well, again, if you look at this diagram here, it's supposed to represent a cylinder, and inside of it is a sphere that perfectly fits inside. So that means that this sphere touches right here on the top of the cylinder, and it touches right here on the side, and right here on the side, and it touches right here in front of us. So you can hopefully visualize what that would look like. It actually is kind of touching all the way around this diameter. So it's the perfect fit. And what does that mean? Well, it means that when we look at the sphere's radius, it means that the radius of the sphere is the same as the radius of the cylinder. And it means that the height of the sphere, sorry, the height of the cylinder is actually the radius twice. So again, this particular cylinder, if it perfectly fits this sphere, has a volume of pi r squared h. But again, h isn't actually h. It's actually 2 times the radius. So we can rewrite the volume of the cylinder as pi r squared times 2r, which simplifies to 2 pi r cubed. So 2 times pi times r squared times r is 2 pi r cubed. That's the volume of the cylinder. And again, what you hopefully discovered in a previous grade, standing in front of like a water table or a sand castle or something, is that this sphere takes up exactly 2/3 of the volume of that cylinder. So for example, if this cylinder was full of water and I pushed or forced this ball in, then exactly 2/3 of the water would spill out because that's the same volume that the ball takes. So that means that the volume of the sphere is 2/3 the volume of the cylinder. And if I do the math on that, 2/3 of 2 pi r cubed is 4 pi r cubed over 3. That's where the formula for sphere comes from. Now, I don't want anyone to worry. You don't have to know where the formulas come from, but I think I'm not doing a very good job as a teacher if I just simply say, here's a bunch of formulas, they're great, use them. I think it's important that you get some sense as to the overall math that goes into things like volume. It's not just arbitrary mathematicians kind of playing around with numbers and letters, that all of these formulas come from somewhere, and they don't come from challenging places in fourth year university math. They come from a basic understanding of shapes. So I think what I want to do is I want to leave this video here. So in this video, all we've managed to do is to discuss the formulas that are relevant for volume. But it seems like a good place to stop the video and to go on to the next video, video number 2, where we'll start to solve some questions involving volume of 3-dimensional shapes. So grab your pencil, your calculator, some scrap paper, and I'll meet you on video number 2.